Hello everyone, let's start with our next topic, that is in open channel flow, that is gradually varied flow. So gradually varied flow, as we defined earlier also, it is a type of steady non-uniform flow, and in this depth of flow varies. So if depth of flow is varying, it means it is a case of non-uniform flow, and but the depth of flow is varying very gradually along the length of the channel. So just for the example, if there is some flow occurring at uniform flow depth, let's say it was occurring at this depth, which is uniform flow depth, and if I'm putting any obstruction here, so because of this obstruction, what will happen now, this depth of flow will increase slowly, and at this point it will reach to the height of the obstruction. And so now this in this zone, the flow is not remaining uniform. It means the depth of flow is varying from section to section. So but the depth of flow is varying very gradually. This length will be in kilometers, so we can define it as gradually varied flow. At the same time, this flow is remaining steady. How is it remaining steady? Because the whatever the flow was coming, and after some time also, if we see, the conditions will be the same. If I take a section here and measure the discharge velocity and depth, it won't change. These parameters will remain same, so the conditions are steady, but these are non-uniform along the length of the channel, so we denote it as gradually varied flow. And so in this case, the losses are considered mainly due to the boundary friction. So whatever the boundaries are, due to the friction only we are considering the head loss. The next point is the component of gravity force in the direction of flow is not balanced by boundary friction. What does this mean? As we know, in the open channel, the flow occurs due to the gravity force, which means the component of gravity force, if I take two sections, so there will be some weight of water in this section. So the, let's say this is theta, this will be w cos theta, and in the direction of flow it is w sin theta, and because of the boundary friction there is some force F. So in the uniform flow, what happens, this driving force, which is the component of gravity in the direction of flow, and this opposing force, both becomes equal. So what happens if they are equal? The flow, there is no external force, so the flow, there is no force to accelerate or decelerate the flow, and which is why the velocity is constant, and so the depth is also constant. So we get the uniform flow condition. And if we leave any flow in an open channel for a long duration, it will try to attain the uniform flow conditions. But as we create some disturbance, so this balance of forces will be disturbed. So it may happen that w sin theta may become greater than f, or it become less than f. So if it is greater than f, so what will happen here? It means the driving force is more and the resisting force is less. So the flow will accelerate in this case. And now if the flow is accelerating, which means the velocity will increase. And for the same discharge, if velocity is increasing, so the depth will decrease. So we will get a gradually varied flow profile in which the depth is decreasing. And in the other case, opposite of this, if the driving force is less than the resisting force, then the flow will decelerate, and hence the velocity will decrease. And if the velocity is decreasing for the same discharge, so the depth of flow will increase. So if the depth of flow is increasing, in that case we'll get some this kind of profile. We'll see the different profiles later. Here we are making some assumptions to study the to make some simplifications in the study of gradually varied flow. First is pressure distribution is hydrostatic. So normally we saw that in uniform flow we can take the pressure distribution as hydrostatic because the depth of flow is not changing and the streamlines are remaining parallel. But in this case, how we suitably apply this assumption, because we don't apply the equation at once to this big section. We will do very small sections and then we'll apply these equations. So for a very small section, this increase in the depth is very negligible, so we can assume the hydrostatic condition. And so for other assumptions are also valid if we are using this case. So Manning's and Chassis formula, these are also derived for uniform flow. But again, if we are taking a very small section, then this depth will not increase considerably, and the channel is also, we are assuming it as prismatic, so the condition will not change, so we can apply the Manning's and Chassis formula. Channel bed is small, so the hydraulic gradient line will remain at free surface. So if the channel bed is horizontal and if we are taking the hydraulic gradient line from some datum z, so it comes out to be z plus y. But if I increase the slope like this, so here the depth, because this component, if the depth is y, so the vertical component will be y cos theta. So the hydraulic gradient line will not be at the top surface, it will be like y cos theta. So but for a very small slope we can take cos theta is equal as 0, so it will be again at z plus y. So this is an assumption. And velocity distribution is invariant, which means that velocity changes whichever are there in the channel, we are ignoring those changes and we are taking one single velocity by putting alpha equal to 1. And the channel is prismatic, as I said before. Now let's derive the differential equation for gradually varied flow profile. So let's draw a section. This is the water flow, so this is the energy line. So if I'm taking some datum here, this level from here, C side, y, this is v square upon 2g. So this is datum head, is pressure head and velocity head. So this represents the total energy line, and from here this is, let's say, making some angle theta. And so if I want to write the total energy at this section, so it will be equal to H equal to Z plus Y plus V square upon 2g. So this is the total energy at this section. Now if I want to know how this depth is varying as we are moving along the channel length, so we want to know this change in the depth. So let's differentiate with, let's say this, in this direction the length is x, so we want to know the variation of y with respect to x. So let's differentiate this equation. We get dh by dx is equal to dz by dx plus dy by dx plus d by dx v square upon 2g. Now in this equation, dh by dx represents the slope of total energy line. Now dh by dx, which means that how this slope of line varying as we are moving in the positive x direction. So we can see here it is decreasing in the positive x direction, and we denote the slope, this slope, as SF, that is friction slope. And because it is decreasing in the direction of flow, we take it as minus SF. dz by dx, it represents the slope of the bed, channel bed. So here again this dz by dx, if I am taking, it represents the slope of this bed. So this is also decreasing in the direction of flow, so I can take it as minus sb. Thus dy by dx represents the change in the depth of flow with respect to the channel bed. So let it be dy by dx, and for differentiating this we can apply the chain rule, and then for here we can denote it. Let's differentiate with respect to y. In this we can write it as qga square and then dy by dx. Now solving it further, the differentiation of this will be q square by 2g and minus 2 upon a cube dA by dy into dy by dx. As we saw did this earlier also, if I take a small strip in this channel, this is the top width, and for that small depth dy, this is the area dA, so dA is equal to t into dy, so dA by dy is equal to t. So if we put this value here, we'll get minus sf equal to minus sb plus dy by dx, and here we'll get minus q square t upon g a cube dy by dx. And if we solve it for dy by dx, dy by dx is equal to sb minus sf divided by 1 minus q square t upon g a cube, which is the required differentiation equation for gradually varied flow. We can write it as, this part we know this represents the Froude number, so we can write it as sb minus sf 1 minus Froude number square. So this equation or the some variation of this equation we'll use to study the various profiles in gradually varied flow. Now the modification of this equation for wide rectangular channel. Say there is a wide rectangular channel like this, and so for a wide rectangular channel what will be different, this, so this is the bed width and depth of flow, so the parameter which we write as b plus 2y, but because this is a very wide channel, so y will be very small compared to b, so we can approximate p is equal to b and neglect this depth of flow, and area will still be given as by because this is in product, so we cannot neglect a number which is in product. So from here hydraulic radius we can write as equal to a by p, which is equal to by upon b, and from here it is equal to y. If I use Manning's equation, I can write discharge as q is equal to 1 by n a r to the power 2 by 3 s to the power 1 by 2. And from here if I put the value of a and r, so q is equal to 1 by n b by y to the power 2 by 3 s to the power 1 by 2. And now for, if I consider a uniform flow, so for uniform flow we know that it will, the flow will be the slope of energy line and bed slope, these slopes will be equal, and from this above equation also we can say for uniform flow these slopes are equal, so dy by dx becomes equal to 0, and so the depth remains constant. So from here we can say that the slope of energy line is equal to the bed slope, and for uniform flow the depth we denote as yn, which represents the normal depth, which is nothing but the depth corresponding to uniform flow. we know that in any channel of a given shape and slope, there will be only one depth at which the uniform flow will occur, and that depth we denote as normal depth. So the discharge now we can write as b y to the power 5 by 3, and for s we can write y will denote as yn for uniform flow, and s we will represent as sb. But for our case, non-uniform flow, this will be y to the power 5 by 3. Now the slope of energy line will be different, so that we represent from SF. Let's say this is equation 1, this is equation 2. Now if I divide second equation by 1, I'll get SF by SB to the power 1 by 2 is equal to yn upon y to the power 5 by 3. So SF by SB is equal to yn upon y to the power 10 by 3. And again, if I take this equation, from here dy by dx I can write as Sp 1 minus Sf by Sb divided by 1 minus q square t by gaq. And for q square t by gaq I can write it as, for a wide rectangular channel, this will be equal to q square, t will be the bandwidth, and gaq is bq yq, and this we can write as q square upon b square divided by g and yq. Q square by b square represents the unit discharge, that is discharge per unit width of bed, q square g yq. And for rectangular channel we know critical depth is equal to q square by g to the power 1 by 3. And if I put the value of q square by g in this equation, so it will be equal to yc cube divided by yq. So from here we got the value of q square t by gaq as yc cube by yq, and sf by sb is equal to yn upon y to the power 10 by 3. Now we put these both values in this equation, so this dy by dx is equal to 1 minus sf by sb is equal to yn upon y to the power 10 by 3 divided by 1 minus yc upon y whole cube. So this is the equation, same modification of the same equation for a rectangular channel. We can derive the same equation using Chassis formula also, and from the Chassis formula we know Q is equal to CA under root RS, and if I put the value of A as By and R is equal to Y, so Q is equal to CBy under root YS. And in the similar way as we solved for these normal depth and depth corresponding to the actual depth corresponding to gradually varied flow, we can find out the equation, and it gives the value as Sp 1 minus yn upon y whole cube divided by 1 minus yc upon y whole cube. Now we will do the classification of different gradually varied flow profile using this above formula. So there are, if you are given with a channel, it means the channel geometry is fixed and given discharge and bed slope. If these things are given, so there will be only one value of yn corresponding to these values and only one value of yc. So we can classify our channel beds corresponding to their comparing these two values. So there can be three cases. First is yn can be greater than yc, yn can be equal to yc, and yn is less than yc. So corresponding to these three cases there will be three bed slopes. So if yn is greater than yc, which means that depth yn, that is uniform depth of flow, is greater than critical depth of flow. So if the uniform depth of flow is greater than critical depth of flow, it means that the flow is subcritical, because we know if the depth of flow is greater than the critical depth of flow, the flow comes out to be subcritical, which we can see in the Froude number formula, which is given as under root gy for rectangular channel. So here, if this value is equal to yc, then it is equal to 1. Now if I put some value greater than yc, then this value will be less than 1, and if I put this value as less than yc, so this value will be as greater than 1. So for this case we are taking yn greater than yc. It means the flow will be subcritical, and yn greater than yc, so for the yn we denote it as normal depth line, and yc we denote it as critical depth line, which means if the flow is occurring at as a uniform flow, it will be coming at this depth of flow, and if the flow is occurring as at critical depth, it will be following this line. So corresponding to these we divided this area into three zones. So the area above the NDL in this case, first of all, this, if it is the subcritical case and NDL is above CDL, so we define it as mild slope. So in mild slope, the NDL is at the top, CDL is below it, and so the zone above NDL we define it as zone 1, and zone between NDL and CDL we define it as zone 2, and zone below CDL we define it as zone 3, and mild slope we represent as M. So if a flow profile is on the mild slope and in zone 1, we will denote it as M1, and similarly if it is in zone 2, M2 and M3. Now the next classification is if the bed slope is such that the normal depth line is below the critical depth line. It means this is the normal depth line and above it is the critical depth line. So in this case the Froude number will be greater than 1, because the uniform flow is occurring at a depth smaller than the critical depth. So if the value of depth is smaller than critical depth, it will be a case of supercritical flow. So in this case we define this slope as steep slope, and in this case CDL is at the top, so the zone above the CDL we will take it as zone 1, and between CDL and NDL as zone 2, and below NDL as zone 3. So if the flow is occurring on the steep slope and in zone 1, we will define it as S1 profile, similarly S2 and S3. Now next is, we considered first was the yn greater than yc and yn less than yc. Third is yn equal to yc. It means the channel slope is such that the uniform flow is occurring at critical depth, means NDL and CDL will be at the same level. So in this case the zone above the NDL or CDL we define it as zone 1, and we used to define the zone between CDL and NDL as zone 2, but there is no zone between CDL and NDL, so we cannot define the zone 2. So here only zone 1 and zone 3 will exist. and we define this slope as critical slope. Now apart from this, there are two more slopes. One is horizontal slope. Horizontal slope means there is no slope in the channel. It means the bed slope is equal to 0. Now if I use the Manning's formula here, so Q is defined as 1 by n, and for wide rectangular channel I can write a y to the power 5 by 3 and under root s, and if I'm taking the uniform flow, this will be Sn and this will be Sp, and now from here yn to the power 5 by 3 is equal to nq upon under root Sp. And now if I'm putting Sb equal to 0, yn is going to be infinite. So we don't know where the normal depth exists. So on a horizontal plane, uniform flow is not possible. In a physical sense, we can see it as, if the slope is horizontal, so the weight of the fluid will be just vertical, so there is no component of the gravity in the direction of flow. It means the uniform flow cannot occur on a horizontal bed. So how this slope is coming into picture? This is because this won't be a standalone case. This horizontal slope will be accompanied by some other slope. Let's say here it may be another slope, so the flow is coming due to the force whichever is there due to this slope which was there before this horizontal bed. So this will be a very small area which is there, so the flow can pass, but the flow cannot occur at uniform depth in this case, as we have seen from this equation. So for this, if we want to define the slope, this is the horizontal slope. So in this case, CDL is here, and we don't know where the NDL will be. It is coming out to be somewhere at a very high distance, so we don't know where it is. So we don't define the zone 1 because the zone 1 will be at the top of the NDL. So we don't have the NDL, so because of that we cannot define the zone 1. So here only zone 2 and zone 3 will occur, and this is horizontal slope, so we define this as, if the flow file is occurring in the zone 2, we define it as H2, and in zone 3 we define it as H3. And one more slope which is there is adverse slope. This will be similar to the horizontal slope only. Adverse slope, this will also be accompanied by some other slope which will be there in the back, which will be there before this adverse slope. So again, from this equation we can see, if the adverse slope means the bed slope is negative, so if SB is less than 0 and if I put the SB some negative value here, so this will be the depth of flow will become imaginary. So again, we don't know where the uniform flow depth will lie. So here again the NDL line will not exist, only CDL line will exist. So here here also there are only two zones, that is zone 2 and zone 3, and so the profiles we define are A2 and A3. Now we'll see the different profiles which occur in these one by one. Now let's start with mild slope. So we use the equation dy by dx for a wide rectangular channel HB 1 minus yn upon y to the power 10 by 3 divided by, we can use either Chezy or Manning's equation here. So for a mild slope, my CDL line is below the normal depth line. So from here, normal depth line is at the top, and there are 3 zones, 1, 2, 3. So if the flow is occurring in the zone 1, so I can say that actual depth of flow, it is greater than yn, which is the normal depth of flow, and it is also greater than the critical depth of flow. And if I check the value of dy by dx from these values, so here we can see the actual depth of flow, which is y, it is coming in the denominator here and here, at both the places. So we can say if the y is greater than yn, so this value will be a fraction, and so 1 minus something less than 1, it will be a positive value. And in the denominator also, y is greater than yc, so this will again be a fraction, and 1 minus something smaller than 1, this is also positive. And bed slope is in this direction, we are considering it as positive, because in the formula itself we have given a negative value to this bed slope. The decreasing we have considered as we did put the sign when we were deriving it. So if it is decreasing now, so we will define it as positive. So from here, dy by dx is coming out to be positive in the zone 1. It means the depth of flow will be increasing. Depth of flow will be increasing in this case. So till what height it will be increasing? So it will not keep on increasing. This condition will be arise due to the fact that we are putting some obstruction in this place. Because of that obstruction, this height has started increasing. So this height will increase up to the height of that obstruction. So in the downstream, we can say it will be defined as and this obstruction, we define it as control section. So it will be defined by the control section. Control section I will talk later in this video only. And in the upstream, if we say in the upstream, this depth will be meeting the normal depth line. So how this is meeting, we don't know yet. So but we can say in upstream, y is going to become as yn. So if y is becoming equal to yn, so from this formula we can again see, if y is equal to yn, then this ratio is equal to 1, and 1 minus 1 is equal to 0. And so here dy by dx will be equal to 0. It means in the upstream side, this will meet the slope will be 0. It means that it will meet the normal depth line. And so this will be our M1 profile. And similarly, we can see for the M2 profile, in this zone, our actual depth of flow is less than normal depth of flow, but it is greater than critical depth of flow. So from here we can, again this formula we can see, y is less than yn, so this ratio will be greater than 1, and 1 minus something greater than 1, this will be negative on the top, and on the bottom y is greater than yc, so this ratio will be less than 1, and 1 minus something less than 1, this will be positive. So net it is coming out to be negative. So dy by dx is negative, which means this will be a falling profile. And in the downstream, what will happen? In the downstream, this, as it is falling, it will at some point it will be equal to the critical depth line. So in the downstream, I can say y is almost equal to yc, and in the formula dy by dx as be 1 minus yn to the power y 10 by 3, 1 minus yc upon y. here it is q. So if I'm using this y when y is becoming equal to yc, it means this ratio will become equal to 1. 1 minus 1, here it will be 0, and something divided by 0, this will be infinite. It means it defines the slope of this line, so at this point this will meet the critical depth line normally. And in the upstream, what will happen? In the upstream, y is almost equal to yn. So when y becomes equal to yn, so this ratio will be equal to 1. So this dy by dx is equal to 0 here, and it means this will meet the NDL again, like asymptotically you can say. And now in the zone 3, in zone 3 what will happen? Dy by dx is equal to sp 1 minus so in zone 3 we can see from here, in zone 3 depth of flow is less than normal depth of flow, and depth of flow is also less than the critical depth of flow, which means that this ratio will be greater than 1 and this ratio will also be greater than 1. So top also it will be negative, denominator is also negative, so it will become positive. And if it is positive, we can say it will be a rising profile. Now what will happen in the downstream? Now we can generalize one thing. If the flow profile is going to meet the CDL, so here we can say in the downstream if it is a rising profile, at some point it will meet the CDL line. So if the flow profile is meeting CDL, which means y is becoming equal to yc, at that point dy by dx will be again infinity. From this equation again we can see that if y is equal to yc, then this will be 0 and this will become infinite. So this will meet the CDL again normally. So this profile will be something like this here. And in the upstream, this flow depth is, if I say y is becoming 0 on the upstream side, so in the practical case y will never be equal to 0, but if we put 0 here and 0 here, so this will be infinity upon infinity, which will be a case of not defined. So we cannot decide from our this observation what will happen here. So it will be defined by whatever the characteristic of incoming flow is, but it cannot become equal to 0. So we denote it as a dotted line here. So these are our three profiles. So for the generalization purpose, we can say here, if some profile is occurring in the zone 1, it will always be a rising profile, and in the zone 3 also it will be a rising profile, and in zone 2 it will be a dropping profile. So if it is rising, it is called as backwater curve, and so 1 and 3 are backwater, and in zone 2 if it is dropping like this, it is called as drawdown curve. To confirm this, let's do another case. So let's do for steep slope. So if it is a steep slope, so the NDL will be below the CDL line. This will be the CDL. Now this is zone 1, zone 2 and zone 3. In zone 1 we can say y is greater than yc, it is greater than yn, and from the formula dy by dx as p 1 minus yn upon y to the power 10 by 3 divided by 1 minus yc upon y whole cube. And if I'm putting y which is greater than yc and yn, which means this ratio will be smaller than 1 and this ratio will also be smaller than 1, so this value will be positive. So again in zone 1, as I said earlier also, this will, if a profile is occurring in zone 1, it will be a rising profile, and in the downstream it will be defined by some other section which is controlling the depth of this structure here, and in the upstream it is meeting the CDL line. So if it is meeting the CDL line, so y will always almost be equal to yc, and when y is equal to yc, this ratio will always be equal to infinite, which means this it will meet the CDL line normally, and this will always be the case. If the profile is meeting critical depth line, it will always meet perpendicularly because this part is coming in the denominator. So whenever we are putting yc equal to y, this will always go infinity. And in the, if I say in zone 2, dy by dx, from here only we can see in zone 2 what will be the case. Y is less than yc, y is greater than yn. When y is greater than yn, which means this ratio here it will be positive because this value is greater than this, so it is positive. And in the denominator what will be the case, y is less than yc, so this value will be greater than 1, and if it is greater than 1, this overall will come out to be negative. So if it is negative, it will again be a falling curve. So how is it falling? We can say in the downstream y is becoming equal to yn. Here you can see in the downstream this is coming equal to yn. So when, as a generalization, I said if y is becoming equal to yn, then the flow profile meets the normal depth line asymptotically. It will go something like this. And in the upstream we know that y is equal to yc, so we can just make it now like this because we know again it will meet normally. So this is the S1 profile, this is S2 profile, and for the S3 profile, zone 3, what will happen, dy by dx, in this zone y is less than yn, less than yc. So if I put it here, this ratio will be greater than 1, so this will be negative upon negative, it is positive. So as I said earlier also, in the zone 3 this will be always be a rising profile, and if it is meeting NDL, so it will meet NDL like this. And in the upstream, if the depth is becoming 0, so we cannot define this area, so we'll show it by a dotted line. So in the generalization, in the zone 1 and zone 3 it will always be a rising profile, and in zone 2 it will be a dropping profile, which is known as drawdown curve. And for another case, that is for critical slope, if we do, so in this case normal depth line and critical depth line both will be at same level. In this case only zone 1 and zone 3 exist. This is 1 and this is 3. So what will happen in zone 1? Let's see first. Zone 1. in zone 1 our y is greater than yc equal to yn, because yc and yn both are equal in this case. So it is equal to sb1 minus yn upon y 10 by 3 yc upon y whole cube. So if I am putting yn and yc as equal, and if I am dividing it by any number, so this whole ratio is going to be 1, because this is the same value, y and yc are equal, and if I am dividing it by single value y, so this ratio will be equal. So from here dy by dx will come out to be sb. Now what does this mean? Now sb, we know sb is the wide slope here, so this is our sb. Now I'm saying this is again a positive value, so this will be a rising curve. So but now how will it go? This is coming out to be sb. It means that what does dy by dx represent? It represents the slope of this flow depth with respect to the channel bed. So now if I draw a line parallel to the channel bed, and if I measure this angle, this is our sb, and now this is also sb, so this line will be horizontal. But it doesn't mean the flow has become horizontal. It doesn't mean so, because this here this slope is decreasing, and so this depth is increasing, so this is actually a increasing kind of profile, which means this is a backwater curve, but this profile will be horizontal, and in the upstream it will meet the CDL or NDL line, and in the downstream it will be defined by the control section. And for the zone 3, again we can say whatever this value, whatever I put here, because yn and yc are equal, so this ratio will still be same. So this is again coming out to be equal to sb, and that is positive. So this will always also be the horizontal kind of curve. So both are rising profile. That means backwater curves, because in zone 1 and zone 3 we saw it will always be a backwater curve, but they remain horizontal. Now two more slopes are remaining, that is horizontal slope and critical slope, adverse slope. So let's do it here. So horizontal, so if the slope is horizontal, as we defined earlier, there will not be a normal depth line, this will just be CDL. So this is zone 2 and this is zone 3, and if we cannot solve it using this equation which we are using in the other cases, it is yn to the power 10 by 3 1 minus yc y2 whole cube, because in this case sb is equal to 0, so it means dy by dx is equal to 0 and y is constant. But this will not be the case, because in any way in this case uniform flow is not possible, so y cannot remain constant. So for studying this we can use our original equation hb minus sf to the power 1 minus fr square. So for the case of we can say if the slope of energy line, if it is greater than sb, it means the bed slope. So if the friction slope is greater than bed slope, it means that if it is equal to bed slope, it means the flow is occurring at normal depth, and friction slope represents the actual depth in gradually varied flow. So if the friction slope is greater than bed slope, so what does it define? That if I'm increasing the slope, so the flow will accelerate, and so the depth will decrease, and so in this case the actual depth of flow will be less than the normal depth of flow because this slope is higher. And if it is less than bed slope, it means that bed slope corresponds to the uniform flow depth. So if the friction slope is less than the bed slope, it means it is something flatter. Or not for the normal bed slope, it is something like this, and now I'm making it flatter. So if the slope is flatter, so flow will retard. So the flow depth will be more. So we can use these two criteria to study these equations. It is simple. If it is the friction slope is greater than the bed slope, then the depth of flow will be less than the normal depth because flow will accelerate. And if it is flow accelerating, it means the velocity is increasing. Velocity increase means the decrease in depth, and the opposite is the case with the this one. So if I use this equation here in the zone 2, what we can see is HB is equal to 0, and SF will always be decreasing in this side. So friction slope will be coming down. That we are considering as positive. So it will be something dy by dx is equal to minus something negative on the top. And for the Froude number, we can say in the zone 2 what will happen. In the zone 2, we know the normal depth is somewhere at the top. In the zone 2, y is less than yn. So when the y is less than yn, but y is greater than yc. So when the depth of flow is greater than the critical depth, and so this is the case of subcritical flow. And if it is subcritical flow, so this Froude number will be less than 1. So 1 minus Froude number will be a positive value. So dy by dx is coming out to be negative. And so if it is negative here, so it means the flow, this is a dropping profile. And as we saw earlier, if it is meeting CDL, so it will meet it normally. In the upstream, we cannot say it will be defined by whatever the structure is here or whatever the other slope from water is coming. It will be defined by that. And in the zone 3 now, zone 3 again we can say from this formula SB is equal to 0 and SF is still positive. So this is something negative. But in the zone 3 what is happening? Our depth of flow is less than critical depth of flow. So when depth of flow is less than critical depth of flow, Froude number is greater than 1. So it is dy by dx is equal to negative upon something again negative. So it is positive. So it is again a rising profile. So if it is a rising profile, it will rise. And as we saw earlier, if it is meeting CDL, it will be equal to, it will meet normally. And from this formula also we can see at CDL this Froude number will become equal to 1 and 1 minus 1. So we will divide it by 0, so this will be infinite. And in the upstream we cannot define because this is again flow depth cannot become equal to 0. Now for the adverse slope, if we want to consider the adverse slope, again this is the critical depth line, and so only zone 2 and zone 3 are existing here. So this is the very similar to what we did earlier. Dy by dx is equal to Sp minus Sf 1 minus Fr square. Now in this case Hb is also negative. So if we take zone 2, so this is on the top, it is negative, and in zone 2 depth of flow is greater than critical depth of flow. If it is, so this is the case of subcritical flow. 1 minus FR will be positive, so this is negative, and so this will be a falling profile and it is meeting CDL, so it will meet it at as normally. And in the zone 3 we know this will again be a rising profile and it will meet it as normally. Here we cannot define it. So these are all the slopes. Now we have to study the interaction of various slopes. Before that we'll see the control section. So the control section is a section where a fixed relationship exists between depth of flow and discharge. So control section can be anything. Now some examples are man-made structures such as weir spillway. So here if we are making a weir or spillway, we know what will be the depth at this point, and corresponding to that depth we can calculate the discharge also. So we know here what will be the depth and what will be the discharge. So from here, if the gradually varied flow profile is occurring, so from this point we will start our calculation, and in which direction this profile will occur, it will depend on whether the incoming flow is supercritical or subcritical. What does it mean now? So let's go back to our Froude number, which is given as, for a rectangular channel it is given as V1 root Gy, but here in this term is known as celerity of the wave, and we define it as C. It can be understood as the velocity of a disturbance which is being created in the channel. So if we take a channel like this, now some flow is occurring in this channel at a velocity v. Now at some point I have created some disturbance here. Disturbance can be anything. If we are making a structure or anything, that will be a disturbance in the flow. So because of that disturbance, that disturbance will propagate in the direction, all the direction. Now in which direction, that we'll see depending upon the speed of that disturbance. Let's say in this direction you are propagating the disturbance at a velocity c. Now there are two cases when f is greater than 1 or f is less than 1. It means that v is either greater than c or v is less than c. Now if v is greater than c, so this disturbance in this channel, it will be propagated at the velocity of v minus c, but v minus c, it will at this velocity it will go downstream. So this is happening when the Froude number is greater than 1. So we can see here, if the Froude number is greater than 1, the disturbance will travel downstream and it is not traveling upstream. So from here we decide that upstream is the control section for supercritical flow. Fr greater than 1, it means it is a supercritical flow, and in this case, if the velocity of the stream will be greater than the velocity of disturbance, so the disturbance will be propagated in the downstream at a net velocity of v minus c, but it will not go in the upstream. So the upstream is the control section for supercritical flow. We'll understand it further when we do this breakdown curve, the combination of flow profiles and how we understand them. And now let's consider a case where the v is less than c. V is less than c, which is the case of Froude number less than 1 and it is subcritical. So in this case, the net velocity in this direction, c is greater. So if I take in this direction, the velocity will come out to be c is greater, so this will be minus V plus C. So if I'm taking in this direction, it is coming out to be C minus V. So it will not go in this direction because C is greater than V. So it will, C minus V will be the velocity with which it will travel in the upstream direction. So I can say if this is the section in the upstream condition, then the whatever the disturbance is occurring, it is traveling in the upstream direction. So the downstream is the control section for supercritical flow. We can understand it like this. If I'm making a dam here, whatever the flow is coming, it was there at uniform depth, but now because of this structure, this depth will increase. And so because this is in the subcritical zone, so this depth is increasing. Like, why is this? So if I know the depth of flow here, so I can calculate the depth in this direction. So I'm starting from a downstream point and moving on the upstream. So downstream is the control section for subcritical flow, and if it is a flow, let's say if I'm putting a sluice gate here, and here it will be, we can say it will be a rising on this side and it will be like this. So what we can see for both the cases here. So on the upstream of this sluice gate, this flow is rising like this. Here it is a subcritical flow condition. So from here we can calculate our depths in this direction, and here it is as it is a supercritical case. So whatever disturbance we are creating here, if we are increasing the depth or decreasing the depth, it will disturb the flow downstream. So here we can say this is the control section. So upstream control for supercritical and downstream control for subcritical. Now there are some combination of slopes which we have to do, which means that there will be combination like mild. First the slope is mild, now it is meeting to a slope which is milder, and similarly it is going milder, which means there are two slopes, and how in their combination how the gradually varied flow profile will occur, that we will study. So first let's do for mild to milder. It means that this is one slope which is mild and it is meeting another slope which slope is, if it is S1 slope, it is S2 slope, then S1 is greater than S2, but both are mild. So if I'm defining what is the Q and what is the channel, so for Q and B, if we know, and it is a prismatic channel, so critical depth line is going to remain the same, it will not change, but the normal depth line changes with the bed slope. In the Manning's equation also, from where we can see 1 by n y to the power 5 by 3 s is power 1 by 2. So if I'm considering it as yn and this is bed slope, so here we can see yn is inversely proportional to the bed slope. If it is inversely proportional, it means if I'm increasing the slope, the normal depth will be smaller, and if I'm decreasing the slope, normal depth will be higher. So here, because the slope is more, this will be the normal depth line, and here the slope is less, so here the normal depth line will be at a higher level, but the CDL line will remain because it is not affected by the slope. Now, because as we defined our control section, so that will come into use here. This is the break in grade at this point. So because as we saw, the downstream is control section for a subcritical flow, and these both are in it is mild slope, so mild slope it is subcritical flow, and downstream is control section for the this subcritical flow. And here, because this is the upstream for this profile, so this profile will not be affected by this control, and it is the downstream of this slope, so this slope will be affected by the this control section. So if we are letting our water flow freely, it will always try to attain the normal depth line, and because this normal depth line is not affected by the control section, so this will just be carried on the normal depth line, but it will be disturbed in this zone, so the flow will try to achieve this normal depth line here. So here we can define our slope as, this is in zone 1 and it is on a mild slope, so we write it as M1 profile. Similarly, next we can do milder to mild. Milder to mild means if this is the slope, but this is our first slope and second slope is something bigger than this. Both are in subcritical zone, but the S1 here is, this is S2, so S1 is less than S2. So again the CDL line will not change, CDL line will be single because the flow and channel conditions are not changing. So this is our CDL line, and on the top of it, if I draw the NDL line, so because the slope is small here, so NDL will be at a higher level, and because this slope is bigger here, so NDL will be at a lower level. This is again our control section. As I said, the control section is the downstream in case of subcritical flow. So again both cases are downstream, but here we don't know whatever is happening in the downstream, but this is the upstream point for this case, so this will not be affected by this control section. So the till here the flow will simply be carried on the normal depth line, and from here to here only the change in depth will occur, so this will meet the NDL like this. So in this case we can see this is again a mild slope, and this is the zone 2, so this will be the M2 profile. Next let's see the steep to steeper. Let's say there is one steep profile. Steep means it will be the slope will be greater than the critical bed slope, so the flow will be supercritical. These are two profiles, and this will be the control section in this case. Now again the CDL line will not change. Now this is S1 and S2. Now S1 is less than S2. So in the case of steep profile, the normal depth line is below the critical depth line. So if this is the critical depth line, normal depth line will be below this. But because S1 is less than S2, so here this NDL, if it is here, so the NDL for this section will be at a smaller level. Now the control section will again come into use. As we know, the upstream is the control section for a supercritical flow. So it means whatever change is happening here, it will not affect the supercritical flow which is happening before this section, but it will change the flow which is happening after this slope, after this control section, because the upstream is the control section for supercritical flow. It means that from here to here, it will simply be coming on the corresponding to the NDL. The flow is coming like this till this point. Now from here the change will start. From here it will try to attain the normal depth line. So it will be joined something like this. So this is NDL, and this zone is between CDL and NDL, and it is on the critical slope, so we define it as S2. Next, let's see mild to steep. Again the CDL will be at the same level, it will not change. And in the mild case, the NDL will be at the top of CDL. This is CDL, this will be NDL, and in the steep case the NDL will be below the CDL line. Now one here we will see two profiles, because the flow before the control section is subcritical, and after the control section it is supercritical. So in this situation, because the downstream is the control section for subcritical flow and upstream is the control section for supercritical flow, so the both of these areas will be affected. And at this point, as the slow changes, so it will again try to attain its uniform depth. So if it is coming at a uniform depth here, it will try to change, and it will touch the CDL line here, and it will again go for the NDL line here. So whenever the flow is occurring and there is no disturbance, it will always try to achieve the uniform flow line. This is the very important thing to remember. So and rest is very simple. Now again we can see this is the mild slope, and between NDL and CDL is zone 2. So and here it again, this is steep slope, and between CDL and NDL it is zone 2. So the profile will be M2 and S2. There will be combination of two profiles. Similarly, we can do for any of these profiles by using the same logic. Next time I'll do some examples from the previous year gate questions. Thank you.